Welcome back. This is an Aleks training video on interpreting the electron configuration of a neutral atom. So we come with an electron configuration address, and an address of an electron is telling you exactly where an electron is. And it looks really weird with all these S's and P's and numbers, and it looks scary, but it's very simple. All it's doing is giving you a shell of electrons, a subshell of electrons, and a number of electrons within a certain orbital. So I need to explain that. When you have electrons in an atom, they are in concentric circles. So you've got a shell or a cloud of electrons close to the nucleus, and then as soon as it is filled with a certain energy level, you're going to get a second one, and then a third one, and you're just going to have these sequential nested clouding shells of electrons. So we're going to start with the numbers. The numbers are telling you the shells. If you look at the periodic table, the rows or the periods of the electron, or the rows on the periodic table, are shells of electron density, where electrons live. So in the first shell, you only have two electrons. You've got hydrogen and helium. Hydrogen and helium completely fill that shell. So that means that there's only two electrons, one electron for hydrogen, one electron for helium, within the first shell. And that makes sense. It's very close to the nucleus. You can't crowd too many electrons there. So it's going to be smaller and then get bigger as it gets farther away. So the 1, when you get to 1s2, is telling you that it's in the first shell. And I only see 1s2, there's no more 1s. What we're going to see is that within a shell, you can have various subshells. Subshells are just locations. Think of the shell like the United States, and each of the subshells would be like states. And if you're going to have an address, you're going to tell the very last address would be the United States. The second address from the end would be whatever state that you're from, and then it just keeps going into more narrow and narrow, and eventually you have the street, and then you have the name of the person in that residence or whatever. Okay, so in the first shell, you have one subshell possible. Okay, if you have more than one subshell, say in the second shell, you're going to have two subshells. We're going to have the S subshell and the P subshell. So there would be two. So let's say in the first shell, there's one subshell possible, and that subshell would be the S. In the second shell, there are two subshells possible, the S and the P. In the third subshell, or in third shell, there's three, so there's a pattern here, the S, P, and the D. In the fourth shell, there's the S, P, D, and F. Okay? Now, a subshell is a more narrow place of where you're going to find electron density, but within the subshells, there are other smaller units where you're going to find electrons. Okay, in the S subshell, you're going to have one orbital, and an orbital I think of as a college dorm room for two girls that don't like each other. It's a room for two electrons, but those electrons are spinning in opposite directions, and they're both negatively charged, and they want away from each other. They're not attracted to each other. They're repelled from each other. So an orbital holds exactly two when it's full. A full orbital holds two electrons with opposite spins. In an S subshell, there's one orbital. That means in the entire S subshell, there is only two electrons possible. In a P subshell, there are three orbitals possible. They all have the same energy level. They're all the same cost to live in that room. And then in the D subshell, there are 5 orbitals possible. And in the F subshell, there are 7 orbitals possible. Okay? Now, let me kind of show you where they are on the periodic table. In the S subshell, we have one room. Think of these as rooms. So I'm going to put this as orbitals. One room with 2 girls each. Okay? So anything in this region anything here in the first two columns are going to be the two electrons found in the first orbital, in the orbital in the s subshell. So if you can see that all of this is going to be your s subshell, and there are two electrons there. There's the first electron here and the second electron here. That means that this is one orbital. This is one orbital. There's one room in the entire S subshell. So in the entire S subshell, there's one orbital, two electrons. That means in the first row completely, in the first shell, there are only two electrons possible. It's in the S subshell, which only has one orbital, which means it can only hold two girls. Okay? Once you get down to the second one, you have S and P. Well, the P's are located over here, and there are 6 electrons. That means there are 3 rooms with 2 girls each. So this would be an orbital, and an orbital, and an orbital. There are 3 orbitals. We're going to see that the P subshell is divided into 3 regions of space where you can find electrons. And you can see a different video to show the shapes of these orbitals, what they would look like. But since there are 6 here, this is the P subshell. There's 6 electrons. That means there's 3 orbitals. These are the Ds. This region right here are the Ds, and there are 10 here. And since there are 10 here, there are 5 rooms. So there are 5 orbitals. And then the Fs are located down here. These inner transition elements, which are located here, stuck in this little groove here, kind of sticking out of the periodic table, are the Fs. There are 14 of these. That means there's 7 orbitals. All right. So now let's see if we can put all of this together. This gives you an electron configuration. It's a long one. Starts with the first shell, 1s2. Okay. Let me erase this so I can write over it again. Okay. All right, so 1s2. 1s2 means that the first subshell is filled. So we have S, 1s1, 1s2. It's interesting, the helium should go right here. The only reason the helium is put on the other side is because its subshell is filled. So it acts like a noble gas. All of these guys have in common that their subshell is filled, all of it. The S and the P, the valence electrons, are full. So when all the S's are filled and all the P's are filled, that is a very, very stable element. So helium is stable, and so instead of sticking it here in this box, they stuck it over here to show you that it was full. But either way, the 1s1 and 1s2 is full. Now we have to go to the second shell, which starts with lithium. So we have here 2s2, so this is 2s1, 2s2, it's full. Now the S subshell is filled. Now any electrons past that has to go into the P subshell, which goes to boron, and we have P1, 2, 3, 4, 5, and 6. So now 2p6 is up to neon. Anything past neon goes to the next level, which is the third shell, and we have sodium and magnesium, so that's 3s2. Anything past magnesium is now into the 3 P's, which is 1, 2, 3, 4, 5, 6. So this element is argon. The element is argon because 3p6 goes from the third shell, the p6 element. Okay? How many electrons does the atom have? Well, there are 18 protons in argon, and since argon is a neutral element, this is a neutral atom, they're going to have the same number. So that means if there's 18 protons, there's going to be 18 electrons. And how many 2s electrons are there in the atom? Well, 2s is here, and there are 2. 1, 2. There are 2s electrons. There are always 2 full. When the S subshell is filled, there'll be 2. When the P subshell is filled, there'll be 6. When the D subshell is filled, there'll be 10. When the F subshell is filled, there'll be 14. So there's a lot more to say about this, but I hope that this gives you some idea. Thank you.